variables. So what we're going to look at today is the so-called triple integrals, where now we're going to be looking at, well, expressions like this. I mean, I'll come to define this in a moment, where we've now got a function of three variables, and we can talk about the integral of that function over a three-dimensional region. Okay, triple integrals are usually denoted with three integral signs just to indicate the dimension, although in a lot of more advanced texts, I mean, even in higher dimensional cases, I mean, it would be obvious that it's a triple integral if we specify the region R as a three-dimensional region without having to write down the three integral signs. But nevertheless, this is the notation we'll use. So we'll have a look at the triple integral. Now, just a word of warning. When I introduced the double integral way back when, so it would have been in Lecture 7, I talked about the problem of finding the volume below a surface and above some region in the xy plane. Now, we could look at a similar problem in one more dimension, but I don't think it's particularly enlightening having to consider things like hypervolumes and that sort of thing. Which is why I made the comment just before that this comes at a good time, right after talking about density functions, mass density functions. So instead, just a simple concept to latch onto throughout this lecture when I introduce this and talk about this triple integral is the context, and as an example of a context is to consider the mass density function f of x, y, and z, which takes on values strictly greater than 0 over some domain of interest. All right, so this is just a comment that I'll make at the start, just to indicate, well, I think this is a better application, just to think about triple integrals rather than volumes, or rather than four-dimensional volumes and so on. It's not really all that intuitive, whereas this is a lot more intuitive, thinking about mass and density functions. Now, I'll talk more about that on the next page, actually, when we look at an example. But just some formalities. Let's get some formalities out of the way. This is what's on this first page of the section. Firstly, the definition. So the definition of a triple integral is, I mean, very naturally extending that of a double integral, and indeed that of a definite integral of a function of one variable, is if we take the sum, and I'll just leave it as a summation where, I mean, really what we're going to do is take a region in three dimensions, chop it up into small cubes, right, and then take this sum over all of those cubes, or boxes if you like. Choose representative points inside each box. Evaluate the given function at each of those representative points multiplied by delta V, the volume of these points. Now, I'll explain later on the next page why or what this has to do with density functions and mass. In fact, I mean, I can give you a clue now. In three dimensions, imagine if we had an object of constant density, then density would just be mass divided by volume. Okay, imagine rearranging that equation so that mass equals density times volume. So it's much the same equation here, that we've got density times volume. But I'll say a bit more about that in a moment. Right, just what I've written here would be an approximation to the value of this triple integral, but what we do is take the limit as delta V goes to 0, or equivalently, the limit as the number of boxes goes to infinity. All right, so there's the definition of triple integral. It turns out we have all these analogous results, like Fubini's theorem. Okay, Fubini's theorem for triple integrals. It's a bit more complicated for triple integrals, right? I mean, Fubini's theorem is much like in the double integral case. It's good news. It means if we want to work out the value of this triple integral, Fubini's theorem means that we don't have to take limits of sums all the time, right? And in fact, what we can do is, in applying the theorem, is to turn that triple integral into an iterated integral, but it's a triply iterated integral, okay? So it's a bit more complicated. So here's here's just one example, right? So if we've got a region in 3 dimensions, so this is just R3, so that just means 3 dimensions, so R being the real numbers. So if we've got a region in 3 dimensions specified by this information, now when I see this sort of description of a region in 3 dimensions, I usually read it in this order. Where to understand properly what this is saying, I usually read this as the set of all points with coordinates x, y, and z, such that the x gets constant bounds, and then given a value of x between a and b, we can define y between these 2 continuous functions of x, and then given x and y in this range, we define z between these 2 continuous functions of x and y. All right? So, I mean, that's just how I read and understand that information, is actually in the reverse order to what's written here. All right? And look, we'll explore this in a lot more detail later on in the lecture. We'll look at one example and exactly how we can apply Fubini's theorem. All right, so the statement is, if we have a region described in this way, then Fubini's theorem turns the triple integral over R of this function f of 3 variables into this iterated integral. Okay, so have a careful look at the order of integration, right? We've got 3 variables now, and compare that, or in particular, compare the bounds with the bounds given in this expression above, right? So this is telling us that we first integrate with respect to z, partially, treating x and y as constant. All right, and when we integrate with respect to z, we integrate that function partially with respect to z, and then substitute in these bounds, the upper and lower bounds. Just as if it were a regular definite integral of a function of a single variable, okay, substitute in for z. So when we evaluate this quantity in the square bracket, we're just left with a function of x and y. And then we're back to an iterated integral of a function of 2 variables, which is what we've been studying for the last couple of weeks. All right? So there's Fubini's theorem for triple integrals. At least this is just in one, corresponding to one order of integration. I'll just mention that Fubini's theorem for triple integrals is given in Stewart on page 1041. In fact, while we're talking about the textbook, let me just scroll right back up to the top for a moment and just make a reference, is that triple integrals are covered in Stewart section 15.7. Okay, so chapter 15 is all about multiple integrals, so double integrals and triple integrals and various applications. Okay, so 15.7 is all about just this introduction to triple integrals. Okay, and more specifically, Fubini's theorem is covered on page 1041. So, I mean, in my lectures, I keep giving you these references to Stewart, so it's well worth having a look at those. All right, but remember what we did in the double integral case when we saw Fubini's theorem. Okay, we saw that for a function of 2 variables with the iterated integrals, there are actually 2 orders of integration, first with respect to x, then with respect to y, or the other way around. Okay, and we called the corresponding regions in the xy plane type 1 and type 2. So now we're in 3 dimensions. We've got 3 variables. There are actually 6 orders of integration, all right, because we've got three variables. I mean, I can list them out here. So dx, dy, dz dx, dz, dy, dy, dx, dz, dy, dz, dx, and dz, dx, dy, and dz, dy, dx. So, I mean, one thing we could do is systematically go through each one and say this is a type 1 region, a type 2, type 3, 4, but that's not what I'm going to do. Okay, so look, just one thing. Of these particular orders of integration, this one that corresponds to the example given above, so dz, dy, dx, so that's one of the orders given here. Okay, and just note, I'll just scroll back up for a sec, up to this description of the region. The types of regions that correspond to that order are where we give constant bounds to x, bounds to y, which are functions of x only, and then bounds to z, which are the functions of x and y. Okay, so for example, if we had, I don't know, pick one of the others. So if we had, if we were dealing with this particular order of integration, that would mean that our y variable would get constant bounds for some numbers c and d. All right. The idea is in this order of integration, integrating with respect to y, that's the last thing we do. All right. So next comes z, and then given a value of y between these numbers c and d, z would be defined between these two continuous functions. I'll just call it g1 and g2 of y. And finally, the description of the region is that the x variable then lies between two continuous functions of y and z. All right, and then it's understood that the bounds of integration, so the first integral would be in this particular order. The first integral would be with respect to x from h1 of yz to h2 of yz. So when we evaluate that integral, it just evaluates to a function. We're just left with a function of y and z, which we would then evaluate in the remaining dz, dy. Okay, so you can see straight away that in 3 dimensions, Fubini's theorem is a lot more complicated than in 2 dimensions. All right, but it's not that much. It's not really that difficult to deal with, especially when you look at ways of describing the region. I mean, you can see this first integral. I mean, you can see there are 2 possible orders where we first integrate with respect to x, 2 where we first integrate with respect to y, and so on. So, I mean, these iterated integrals, you can break down into pairs of iterated integrals, if you like, and think about it that way. But anyway, this is just to give you a bit of a taste of how we're going to deal with triple integrals from now on, okay, and what's required. All right, so really it's all about Fubini's theorem in evaluating the triple integrals. Let me just zoom in a little bit. So, on page 93, we've got this example that says, find the mass of a rectangular block with these dimensions if the density is given by this function here. So rho naught and alpha are just taken to be constants in this case. But before we look at the example, I just want to elaborate upon the definition of the triple integral that I gave earlier on the previous page. And in fact, because this example, I mean, it's a perfect context for introducing the triple integrals. I mean, this example is talking about density functions and finding the mass and so on. So let me just elaborate upon the definition and this context of finding the mass of an object given a density function. So in 3 dimensions, let's say we've got a continuous All right, and so this discussion is going to progress much like the discussion we had in yesterday's lecture about density functions and mass of objects and so on. So let's say we've got a three-dimensional continuous density function. Rho, because we're in 3D, that gives the mass per unit volume now. So remember in yesterday's lecture when I introduced it in one dimension, we were talking about mass per unit length. In 2 dimensions, mass per unit area. Now we're talking about mass per unit volume because we're in 3 dimensions. And this function, rho of x, y, and z, is going to be given as the limit as delta v goes to 0 of this ratio of delta m with delta v. All right. Now I guess I should explain what these things are. So well, I'll just say where. So let's say we're in 3 dimensions and we've got a region. Could look something like a potato. I mean, I always find myself reverting to analogies with food when it comes to considering these. But anyway, in 3 dimensions, let's say we've got a region, looks something like a potato, and what we're going to do is dice it up. Okay, now I'm not going to try and draw a potato with a 3-dimensional mesh. Okay, but the idea is we're dicing it up, so a bit like a diced potato. Yes, I'll make that comment in the notes. So one of these boxes might look like this. So if I'm just drawing a 2-dimensional projection, right? So these are meant to be little 3-dimensional cubes. Okay, so what we'll do is choose a point inside one of these boxes, okay, and that point has coordinates x star, y star, and z star. So this is what I refer to always as a representative point of this particular box. All right. Now, what we'll do to understand this, I'll actually think about it in a different way, is think, well, what's the mass of one box? Okay, and this is what I'll call the quantity delta m. So what I've written here, this delta m, is just the mass of one of these potato cubes. Right? So what we can do is make an approximation to this mass using the definition of density function. So what I'm trying to do is just offer a bit of an explanation of what this definition means. Okay, the mass of one box. So what we'll do, first make an approximation where we've chosen our representative point with these coordinates. So I'll assume this box here is pretty small, and given that we've specified the density function is continuous, what that means is as we move around inside this box, right, whatever point I happen to choose, right, the value of the density function is not going to change by much. Right? So if we were to change this point, move it around inside the box, the value rho evaluated at those points as we move around inside the box is not going to change by much. Right? It's not going to be jumping around all over the place. Rho is a continuous function. I've stated that at the start. So it's not going to change by much because this box is tiny. All right. So as an approximation, we'll just assume that the density function takes on a constant value over that box. Right? And that the value we'll choose is the value of the density function at this representative point. Okay, so as an approximation to the mass of one of these boxes, we'll just rearrange this equation. Now, if this were constant density, that really would be mass divided by volume, right? No limit to consider in that case. So what we'll do is take the mass of one box to be approximately the density function evaluated at that representative point multiplied by the volume of the box, delta V. So that's what these quantities are. So once we've diced up our potato, the delta M is the mass of one of those boxes, and delta V is the volume. All right, so there's the mass of one box. So what we can do, remember it's a continuous density function, what we can do is then work out an expression for the total mass simply by summing up over all boxes all of the individual masses, delta M, that I've just written there. But this is just the sum over all of those boxes of rho, so the density function, at all those representative points inside each box, times the volume. All right, so we've worked out the mass of one box. Okay, so we just repeat that process over all the little bits of diced potato. Okay, and this gives us an approximation to the total mass, is just the sum of all of those potato cubes, right, summing up over the masses of each potato cube, where each mass is given by a density function times volume. All right, but now hopefully you can see, have a look at the definition of triple integral I gave on the previous page. We take the limit as the volume of these boxes go to 0, and then we end up with this expression for the mass is that it equals the triple integral over the region of this density function. Okay? So look, that's just some general discussion to help you understand the definition of triple integrals. So you know what I mean now when I say this is in 3 dimensions. It's quite natural to consider or to think about triple integrals in terms of mass density functions, at least just as a first port of call to understand that definition. All right, so look, we've got an example here where we're asked to find the mass, which now we've just worked out is the integral of the density function. And now what we seek to do is apply Fubini's theorem. All right, so in this case, the density function that's given for the example stated at the top of the page, the density function is just rho naught plus alpha x, y, z, where rho naught and alpha are constants. Okay, but now the thing is, in the statement of the problem, let me just scroll back up to the top of the page here. In the statement of the problem, these bounds all happen to be constant. So just like in the double integral case, that's telling us that it doesn't really matter what order we choose. All 6 bounds of those iterated integrals in the 3-dimensional Fubini's theorem will be constant. So it's not going to matter what order we choose. So for example, we could choose to integrate first with respect to x. So we're given the bounds of x to be 0 and L. Then with respect to y, and at the top of the page, I'm just reading this off the information that's given at the top of the page, from 0 to w. And finally, with respect to z, between 0 and h. All right, so now this is a triply iterated integral. So it's exactly the same idea as in double integrals. We work from the inside out. So what that's saying is the inner integral is with respect to x. So we're going to integrate this function with respect to x, treating y and z as a constant. Okay, so these outer 2 integrals are not going to change, just in this first instance. And integrating with respect to x, we'll end up with rho naught x plus a half alpha x squared yz evaluated from x equals 0 to x equals L. And so you can see when I substitute in those bounds for x, I'm just going to be left with a function of y and z. Okay, so substituting in those bounds, we'll end up with rho naught L plus a half alpha L squared yz, and substituting in that lower bound just gives 0 everywhere. All right, so now all we're left with is a doubly iterated integral, first with respect to y, then with respect to z. And so that's the sort of thing I've been talking about for the last couple of weeks. All right, so, I mean, the rest should be pretty straightforward. Right? What's new in this lecture are these triply iterated integrals coming from Fubini's theorem. All right, so look, the result that you get is rho naught times L, H, and W plus alpha on 8, L squared, W squared, H squared. So one thing you can see here is if alpha was 0, what would that density function look like? So if alpha was 0, the density function would just be the constant rho naught, and if alpha was 0, that term in the final answer wouldn't be there. And so this leading term, the rho naught LHW, is just the constant density term that we'd expect. So this is saying that in that case, if alpha was 0, the mass would be the constant density times the volume. All right. In this case, we're just calculating the mass of that rectangular block. Okay, so it's not always that easy, right? Sometimes we can get more complicated regions. And so in that case, how can we deal with them? Well, we still use Fubini's theorem, but it can be a little bit more challenging to apply. So one thing, with this next example, it says evaluate the triple integral of this function z over the region in 3 dimensions, over the region R, bounded by these surfaces. So x equals 0, y equals 0, z equals 0 are all just the coordinate planes. And this plane x plus y plus z equals 1. So this region's not too bad. In fact, I can draw a diagram of the region. So draw up the axes x, y, and z. So here I've drawn in all 3, I've already drawn in the 3 coordinate planes, right? Remember x equals 0 is the yz plane, y equals 0 the xz plane, and z equals 0 the xy plane. But this 4th plane, x plus y plus z, well, I can see when, if I set 2 of the variables equal to 0, I can see where it's going to intersect the coordinate axes. So for instance, when y and z are both 0, x is 1. When x and z are both 0, y is 1, and so on. Actually, I might just make it a bit smaller, just for the purposes of the diagram. Okay, so here's x equals 1, y equals 1, and z equals 1. Okay, so the surface x plus y plus z equals 1 looks something like that. And I can see this tetrahedron shape, so that's solid with four sides, which is now the region of integration, right? So dealing with this triple integral that we have to evaluate, that 3-dimensional region is the region of integration. So I'll call, well, it's labelled as R. So what we want now is to apply Fubini's theorem, right? So what I want to do, first of all, is determine an expression for that region in this form as the set of all points with coordinates x, y, and z such that, and then give bounds on the variables. Now, I can try and do this 6 different ways, corresponding to the 6 different orders of integration. So what I might do is start by giving constant bounds to z. So this is a rather complicated procedure, or not complicated, but there are a few steps involved. So I want you guys to sort of pay careful attention to each step along the way so that you can understand where I get these bounds from. So firstly, I have a look at the region in 3 dimensions, and I can see that the region lies entirely above the xy plane, which will give a lower bound for z, and the plane z equals 1. So I'll draw that in here. So there's the plane z equals 1. All right, so my region lies entirely between those two planes, those two horizontal planes, z equals 0 and z equals 1. So I've tried to draw that in to indicate that. And in fact, you could sort of close off those planes if you want, just to help you visualize that. All right, so just specifying this information, it's not giving me anything like the region so far, right? It's just saying this is just, if I just give z between 0 and 1, that's just saying all points between those two planes. What I need to do is give some more information. So give bounds for one of the other variables and start narrowing down that three-dimensional region. So the next variable I'll choose, so you could do this in any other order, by the way, so I'm just going to choose this particular order, is we'll look at the bounds for x. So given these bounds for z, what are the bounds for x? So what we'll do is look at this three-dimensional region projected onto the xz plane, right? Because that's what I'm interested in, x and z at the moment. I'm not concerned with y just yet. So since this surface, this plane, has equation x plus y plus z equals 1, if I set y equal to 0, the equation for that line there in the xz plane is just going to be x plus z equals 1. All right, and so given any value of z between 0 and 1, what I'm looking for are bounds for x. So I'm just looking in the xz plane here. And so what I've drawn are these horizontal lines, okay, or at least lines which are parallel to the x-axis that lie in the xz plane, that allow me to see that the lower bound for x is going to be 0. So all points on these lines that I'm drawing with little arrowheads, the minimum value of x always lie on the z-axis, and the maximum values for x, just in this triangle in the xz plane, always lie on that line with equation x plus z equals 1. But I want to rearrange that so it's in the form x equals some function of z. So I just rearrange that to the form x equals 1 minus z. Okay, so now I've got these two sets of bounds for the variables z and x. So what is that telling me about the region? If I were to just say, all right, the region lies within these two bounds for x and z without giving any bounds for y, what is that telling me? Well, here's where it starts to get complicated and stretch my artistic abilities. What this is telling us is that our region lies somewhere, so I'll just extend these axes off to the edge, off to in both directions. What this is telling us is our region lies somewhere in this infinitely long tube which runs parallel to the y-axis that has a triangular cross-sectional shape. That's all this information is telling me so far, right? So I acknowledge my diagrams are not great, but what I'm trying to do here is highlight that this infinitely long tube which runs along parallel to the y-axis. Okay, that's what I'm describing just by giving these two bounds on x and z. I'm not giving any bounds on y, right? So actually, this tube, if you like, extends to all values of y. And I'm just saying that the region I'm interested in lies somewhere in that tube. So what I need to do is give one more set of bounds. The variable that's remaining is the y variable. And this is where my bounds for y, in general, are going to be functions of x and z. And so what those two bounds will give are two surfaces. Y equals some function of x and z as the lower bound. Y equals some function of x and z for the upper bound. And that's going to give me two surfaces which chop that tube in two places and uniquely determine the expression for that region, the expression that I want. So, all right, what are the two slices of that tube that I need? Well, one, I mean, we're given it here, the plane y equals 0. Okay, that's this plane I've highlighted, this triangle in the xz plane. All right, so if I chop that tube at y equals 0, that's actually going to be the lower bound for y. All points with the minimum values of y in this region must have y equals 0 and hence lie in the xz plane. All right, but what about the upper bound for y? So that's going to be my first chop at y equals 0. The second slice of this infinitely long tube will be this plane here. Okay, and I know that has equation x plus y plus z equals 1, which I can rearrange and write it in the form y equals 1 minus x minus z. Okay, so you see each step along the way I'm narrowing down what the description for the region is. Okay, so this uniquely determines all points inside the region and gives appropriate bounds. And this is why I said in my comment earlier about how I think about how these bounds work. I always think about the constant bound first. Right? Once more, it's telling us that the z variable, or all points in the region, are bounded between z equals 0 and z equals 1. So stating this first bit of information is just saying the region lies between the two planes. Specifying that second bit of information is saying that the region not only lies between those two planes, but somewhere along this infinitely long tube parallel to the y-axis. And then specifying this third bit of information, which are the bounds for y, is telling me the two places where I chop that tube, okay, allowing me to completely describe the region. Okay, so that's the hard part done, right? Now I can apply Fubini's theorem, right, and write down the triple integral of this function z as an iterated integral. Now, the order I've chosen means we first integrate the function z with respect to y from y equals 0 up to 1 minus x minus z. Then, with respect to x, from 0 to 1 minus z, and then with respect to z, from 0 to 1. Look, guys, maybe as an exercise, why don't you try working out how to apply Fubini's theorem for this example, but in another order, using another order of integration, right? And see if you can work it out. Okay, so now it's just, this is the easy part of the calculation, right? The hard part is working out the bounds of integration, is working out this description for the region. The easy part is now evaluating the integrals. It's an iterated integral. There are three variables three integrals I need to evaluate. So first, I work from the inside out. I integrate with respect to y. And the two outer integrals are not going to change. So integrating z partially with respect to y, I'm going to get yz evaluated from y equals 0 to y equals 1 minus x minus z. Okay, and then we've got dx, dz. So substituting in those the upper and lower bounds, we're just going to end up with a doubly iterated integral. So substituting in the upper bound, we'll end up with 1 minus x minus z, all times z. Substitute in the lower bound, that's just 0, dx, dz. Okay, so now, I mean, this is just a two-variable polynomial in x and z, so that's reasonably straightforward to integrate. And I won't go through the details of that. But the point is now we're just left with a doubly iterated integral, which is exactly what I've been talking about for the last couple of weeks. And check the answer works out to be 1 over 24. Okay, so guys, the hard part in all of these triple integrals, right? even though Fubini's theorem is good news, right, that we can evaluate the triple integral by evaluating an iterated integral, we still have to work out the bounds for those iterated integrals. And that's always the hard part. Okay, so look, just this next example is about changing the order of integration. Now, I gave a similar example for double integrals, and I think this is a really good exercise just to help with your understanding of triple integrals and Fubini's theorem and the regions and so on. So I really like these sorts of examples. You'll notice some of the past final exam papers that I've written have questions like this on them. One of my favourites. Okay, so we're given now a triply iterated integral. We know that there are 6 possible orders of integration. In fact, I think this might come from one of the examples or one of the problems in Stewart at the end of section whatever it was, 15.7. So you might like to have a look at the problems at the end of that section. But whereas in Stewart, it says here's an iterated integral, give all other 5 orders of integration. What I want to do is just show you how to work out 2 other orders of integration. And just note the difference. So we start with dz dy dx. And then one of the orders is just by swapping the order of x and y, and the other order is taken by swapping the inner 2 integrals, y and z. So actually with that strategy, if you just swap pairs one at a time, that allows you to work out all possible orders of integration. So I just want to outline the strategy. So let's have a look at how we'll deal with the first one, dz dx dy. Let me write the integral. I'll just write this out one more time. I want to annotate it a little bit. So we've got a function of 3 variables, and we've got dz, dy, dx. Now remember, this is an iterated integral. If I evaluate that inner integral with respect to z, I'm going to be left with a function of x and y only. So let me call that function g, right? So we'll let g of x and y be this function, integral from 0 to 1 minus y of f of x, y, and z, partially with respect to z. All right? So that's going to evaluate to a function of x and y, and then that implies that the integral is then just this iterated integral of the function g of x and y dy dx. All right, so actually there's no difference in this example. So what I want to do is swap the order of x and y. So this is exactly like changing the order of a double integral. So in fact, we've already covered we've already covered that detail, and indeed there's nothing really more I can say that's not already been said in lecture 10. I think it was lecture 10 where I talked about swapping the order of integration. But nevertheless, I can just remind you how it's done. So in the xy plane, so this is saying, all right, the region of integration is for all values of x between 0 and 1. So here's x equals 1. X equals 0 is just the y-axis. Then the bounds for y are from y equals the square root of x. So that's going to look something like that. Y equals root x. And y equals 1 will just be this line here. Y equals 1. All right, so the region of integration in the xy plane just looks like that. And what I want to do is reverse the order of integration to dx dy. So in other words, I want to give constant bounds for y. I can see the region lies entirely between y equals 0 and y equals 1. So they're going to be my bounds for y. But then given those bounds for y, the x variable, the minimum in the region, always lies on the y-axis. So that's x equals 0. And the maximum value of x on each of these horizontal lines I'm drawing always lies on that parabola. But I need to represent that parabola in the form x equals some function of y. Right? Given that it has equation y equals root x, I can just rewrite that as x equals y squared. And so y squared is then going to be the upper bound. So remember, I've already defined g of x, y up here, so I can write that in straight away. And then we've changed the order of integration in that particular order, right? Just by substituting back in that expression for g. All right, so that one's not too difficult. I mean, there's nothing new, there's nothing conceptually new there. Only slightly more complicated is this next order, where I want to change to dy, dz, dx. So that involves reversing or changing the order of integration of these inner two. All right, so what I can do is something similar to the previous example. I can just point out, actually let me just scroll back up to this statement. I can just point out that when I evaluate these two integrals, the two inner integrals, first with respect to z and then with respect to y, I'm just going to be left with a function of x, right? So I'll call that function h. So I'll let h of x just be this integral, which are the inner two integrals. So from root x to 1, and then integral from 0 to 1 minus y of f of x, y, z, dz, dy. All right, so that the integral I'm interested in is just the integral of the function h from x equals 0 to 1. All right, now what I can do is treat this as a double integral for any value of x between 0 and 1, or rather for each value of x between 0 and 1. So I'll say for each x in the interval from 0 to 1, we have, I'll call it the region of integration in the yz plane. I'll call it d subscript x because it will depend on my choice of x. Is just going to be the set of all points with coordinates y and z. Actually, it's not in the yz plane, but it's in a plane parallel to the yz plane, corresponding to whatever value of x I choose between 0 and 1. All right, so this is telling me that the bounds for y are root x and 1, and the bounds for z are 0 and 1 minus y. So I can draw a diagram of this in a plane parallel to the yz plane. So I'm going to treat x as a constant. And that's really the key here, because what I'm doing is taking a slice of my three-dimensional region corresponding to that given value of x. Okay, so let's have a look. What are the bounds for y? We've got y equals root x, so I'll just make that this line here, y equals root x, and y equals 1 I'll put here. Remember, I'm treating x as a constant, so you give me a value of x between 0 and 1, say x equals 1/2, and that's the diagram I'm drawing in this case. All right, now what about z? Well, given those values, those bounds for y, so somewhere between these two vertical lines, the bounds for z are z equals 0, which is the y-axis, and z equals 1 minus y, which is going to look something like this, right? Z equals 1 minus y. And so when y equals 1, it's 0. Yeah, that's right. So what I want to do now is change the description of this region. It's still going to be the set of all points with coordinates y and z, but now I want to give bounds for z first, which are constant, but in general they'll be they could depend on x. So the lower value I can see is z equals 0, right, the y-axis. So this is the region in here. This is the region that's given, and this is the order that I want. So z's from 0 up to that maximum point there. Now, on z equals 1 minus y, when y equals root x, that must correspond to z equals 1 minus root x. Sorry, that's 1 minus root x. So that's going to be the upper bound for z. And then for y, given those bounds for z, the lower bound for y will always lie on this vertical line here with equation y equals root x, and the upper bound will always be on this line with equation, well, not z equals 1 minus y, but y equals 1 minus z. Okay, and then that allows me to read off the bounds of integration. So the the outer integral is with respect to x from 0 to 1, and now I've changed the order of integration of the inner two. All right, so first with respect to y, from root x to 1 minus z, and then with respect to z, from 0 to 1 minus root x. All right. So guys, look, that's all I wanted to say. Well, in fact, I did want to show you some MATLAB, but unfortunately I'm out of time. But that's okay. I mean, I might bring it along to the next lecture. So this is the last lecture before the break. The first lecture we'll have will be the 8th of April, I think. Yeah. Okay, so see you then, and enjoy the break.